You ever wonder how they get the caffeine out of coffee to make decaf? Or, how life-saving medicines get purified? Well, it all comes down to one of the biggest challenges in chemical engineering. How do you separate stuff cleanly and, most importantly, efficiently? Today, we're going to dive into a really powerful technique for doing exactly that, and it's called liquid-liquid extraction.
Okay, so picture this. You've got two liquids that just don't mix. Think oil and water. One of them has something valuable dissolved in it, and your job is to get that valuable thing into the other liquid. To do that, you pass them through this whole series of stages, kind of like a cascade of mixers and settlers. But the big question, the million-dollar question, is always, how do you design this whole setup for maximum efficiency?
The key to the entire design really boils down to finding one single number, and we call it N. N is just the ideal number of those separation units or stages that you need to get the job done right. If you have too few, well, your separation is going to be incomplete. But if you have too many, you're just wasting a ton of money and energy. It's all about that sweet spot.
So, how in the world do we find that magic number N? You might think there's just one universal formula you can plug everything into, but it's really not that simple. The path you actually have to take to find the answer, it depends completely on the unique properties of the very chemicals you're trying to pull apart.
So the deciding factor, the thing that tells you which way to go, is something called the equilibrium relationship. The best way to think of it is like this. Imagine you've got some sugar dissolved in water, and then you pour in some oil. The question is, how much of that sugar is naturally going to move over into the oil phase? That natural distribution, where things settle, that's the equilibrium. And it's a fundamental property of the chemicals themselves.
And this right here brings us to the fork in the road. It's the central idea of this whole explainer. If that equilibrium relationship is a nice, predictable straight line, what we call linear, then we get to take a mathematical path. We use the analytical method. But if that relationship is a curve, non-linear, we have to take a totally different, more visual path, the graphical method.
All right, let's head down our first path, the analytical method. This is the route we get to take when our chemicals are, let's say, playing by a simple set of rules. When their equilibrium relationship is that nice, predictable straight line. This approach is all about solving the problem with precise calculations, by the numbers.
So, this entire method is built on one super simple but really powerful idea, the solute mass balance. Seriously, just think of it like basic accounting for a single one of those stages. The amount of the chemical that goes in must equal the amount that comes out. It's a fundamental law of conservation. You can't create or destroy matter here.
So, we start with our basic accounting rule. What goes in must come out. Now, because we're on this straight line path, we can describe that relationship with a really simple equation, y equals mx. Plugging this little equation into our mass balance is the first major step toward building our final formula.
Okay, at this point, the math can start to look a little messy. So engineers do something really clever. They basically bundle up a few of the numbers that keep popping up, the flow rates and that constant m, into a single shortcut term called alpha. It's just a simple substitution, but it cleans up the equation and makes it way easier to work with.
From there, it's really just a series of clever algebraic moves. We're not going to bore you by going through all the math, but just know that the end result is this really powerful formula that can predict the concentration of our chemical at any stage you want in the whole process.
And here it is, the payoff. After all that math, we get this, a single, elegant formula to calculate N, the total number of stages. You literally just plug in your starting and ending concentrations and that alpha value we talked about, and bam, the answer pops right out. It's pretty amazing.
But, and this is a really big but, there's a catch. This beautiful formula only works under a very specific set of conditions. You need a multi-stage process where the two liquids are immiscible. Again, they don't mix, like oil and water. They also have to be flowing in opposite directions, which we call countercurrent. And, of course, the big one, the chemistry has to follow that perfect straight-line relationship. So what happens when the chemistry isn't so simple? When that relationship is a curve instead of a straight line? Well, that's when we take our second path, the graphical method. And for this one, we can pretty much put away the calculator because we're going to solve the problem with our eyes. Now, the beauty of this method is its wonderfully elegant three-step process. It's so straightforward. First, you plot your lab data on a graph to make your equilibrium curve.
Second, you draw a straight line, we call it the operating line, that represents your process from start to finish. And third, you literally draw steps between those two lines to count up the stages. That's it.
To really see how this works, let's look at a real-world problem. Our mission, should we choose to accept it, is to pull benzoic acid out of a liquid called toluene, and we're going to use pure water to do it. This is a classic example where the chemistry is nonlinear, so the graphical method isn't just an option, it's our only option.
Okay, so this is our starting point, a simple table of raw data from the lab. It shows how the benzoic acid concentration in the toluene, which we're calling X, relates to its concentration in the water, which we're calling Y. These numbers right here are going to become our equilibrium curve.
Now, the problem tells us that we need to recover 98% of the benzoic acid. And that target is absolutely crucial because it lets us calculate the exact starting and ending concentrations for our entire process. Those 2 points are what will define our operating line on the graph.
And here is where the magic really happens. That dry table of numbers, it transforms into this incredibly powerful visual diagram. The blue line, that's our equilibrium curve. We plotted it directly from our data. The green line, that represents our process, connecting our start and end points. All of a sudden, the entire problem is just laid out right there in front of us.
And now for the most satisfying part, honestly. We start at the top of our green operating line, we draw a horizontal line over to the blue equilibrium curve, and then we go straight down back to the operating line. That's one stage. And we just keep doing that, over and down, drawing these steps all the way down the graph. So after we've drawn all the steps it takes to get from our starting point all the way down to our target endpoint, the big question is, how many steps did we actually have to take?
7. That's it. By simply counting the steps on the diagram, we find our answer. We need exactly 7 ideal stages to hit our 98% recovery goal. No complex formulas needed, just a clear, visual count.
So we've just walked down 2 very different paths, right? One was pure math, the other was purely visual, but they both led us to the same kind of answer. And this brings us to the most important takeaway of all: why knowing which path to take is so critical. It really all comes down to using the right tool for the job.
Here's the crucial point I want you to remember. The choice between the analytical and the graphical methods, it's not a matter of personal preference. It's not about which one you like better. It is dictated by the physical reality of the chemical system you're working with. The chemistry itself tells you which path you have to take.
And you know, that leaves us with a bigger question. This choice between a precise formula on one hand and an elegant visual on the other, it isn't just for chemical engineers. I mean, think about it. In what other areas of your life, maybe managing your finances or planning a big project, do you face a similar choice? When is it better to just crunch the numbers, and when is it actually better to just draw the picture?